Testing on YouTube, testing on YouTube, testing on YouTube, testing on YouTube. Testing on YouTube, testing on YouTube, testing on YouTube. It's not working on YouTube. Come on. Testing. Testing. All right, I think it's working. All right, working on YouTube. Let's now see if it works on X. How's it? How's it going, Sarah? How's it going, Aries? Let me spit out this gum. All right. Broadcast is not available. Oh no. Come on. Come on, Elon. Why doesn't this work? It's all your fault. All right. All right, I think we're getting there. Turn this a little bit. Does it work? Does it work? X is still not working. Broadcast is not available. Okay, there we go. It was just delayed. All right. Perfect. How's it going, Stuart Patterson? Bonjour, economic sanity. Let's get this bad boy started. I'm slowly getting a little bit better at the didgeridoo, so hopefully those work a little bit better. 12 a.m. in Sydney. I appreciate you watching all the way from Sydney. All right. We got a stream today for you guys called OpenELM, Phi-3, and LLaMA-3. So we're going to be looking at 3 different papers today. All 3 of these papers are pretty short. So this paper is 10 pages, 12 pages, and then you got this one here at 7 pages. So 3 little short papers that kind of all came out. All 3 of these papers have to do with open source models from one of the different tech giants. And they're kind of like benchmark, eval, kind of performance type papers. You know, a lot of the paper is just tables where they basically compare the scores. But they're also a good kind of summary of like what all the different tricks that people are using. And maybe it starts to allow us to ask questions about what things matter, what don't things matter. So we're going to kind of use these as a talking point and try to think about some cool ideas. I don't know. How's it going, Ed? So the 3 papers that we're going to be reading are OpenELM, an efficient language model family with open source training and inference framework. This is a paper from Apple, released on the 22nd of April, so just this week. The other paper we're going to be reading is Phi-3 Technical Report, a highly capable language model locally on your phone. This is Microsoft. So we got an Apple paper, we got a Microsoft paper, and this is the 23rd of April, 2024. And then the third paper we're going to be looking at is how good are low-bit quantized LLaMA-3 models, an empirical study. This is not a paper officially released by Meta. This is released by a different group, but it has to do with the LLaMA-3 release, which I think is the other big open source language model that has been released and making waves recently. So we're going to kind of use it as a stand-in for the Llama Meta Open LLM. Also released on the 22nd of April. Tomorrow is my math paper and I'm watching your stream. Ooh. I don't know, maybe you should study, but I don't know, maybe you need a break from studying so you can hang out with us for a little bit. All right. So we're going to start off with OpenELM. OpenELM here, you got a bunch of different people here at Apple. And OpenELM is an open source language model, which is interesting because Apple is doing a lot of open source. You know, we reviewed a vision language model that Apple released. Apple actually calls them LLMs, multimodal large language models. But it seems like Apple is being very open source. So Apple's kind of joining Meta in the open source side of the battle, right? And then on the other side of the battle, you have OpenAI and Anthropic and kind of the closed source people. So you're seeing this kind of like closed source contingent versus the open source contingent. And open source used to just be Meta, but now it seems like Apple's part of it too. So good for the open source people. You want some of those heavyweights on your side. All right, let's start off with the abstract here. OpenELM is a state-of-the-art open language model. It uses layer-wise scaling strategy. For example, with a parameter budget of approximately 1 billion parameters, which is quite small, you know, like 7 billion parameters are considered small, so 1 billion parameters is basically cell phone size. OpenELM exhibits a 2.36% improvement in accuracy compared to ULMA, which is kind of like a previous open language model. Requiring 2 times fewer pre-training tokens. This is something that people have been focusing on with this release, is the performance that we're getting in OpenELM despite the lower amount of training tokens, which is kind of weird, you know, because this kind of like breaks a lot of the intuition around scaling laws where, hey, how can you have a model that's both smaller and trained on less tokens and somehow it's better? But we're going to see how they manage to do that. All right. Divergent from prior practices that only provide model weights and inference code, right? This is another important point, is that a lot of times people will say, hey, we're an open source model company, but really the only thing they release is the weights and the inference code, which means you can use our model in inference, but they don't really tell you how they trained it. They don't tell you the mix of data that they use. They don't tell you any of the kind of tricks that they developed for training these, right? Because as we're seeing, the training process is becoming increasingly complicated. You have these kind of like multi-step training curriculums, and you also have all the kind of complexity of training in a distributed way on these giant clusters. So even though people say they're doing open source models, a lot of time they're not. And Apple here is saying, okay, we're going to actually tell you everything that we did. They don't quite tell you everything, but it's certainly more information than other large players are giving. And this is exactly what they did for the vision language model that we reviewed as well. So Apple going like full open source. So they include the complete framework for training and evaluation of the language model on publicly available datasets, including training logs, multiple checkpoints, and pre-training configurations. They released the code to convert models to the MLX library. So MLX is how you do inference and fine-tuning on Apple devices. So if you're trying to fine-tune things on a Mac or run things on your MacBook or on your iPhone, this is the library that you would use. And there's the GitHub for it. How's it going? 2ARX, James McLean, Lil Kim. I don't exactly know how you do that. And then Tarun. How's it going, everybody? Okay, so generally we skip the introduction section here because it's not super important, but they mention again this idea of layer-wise scaling, which we're going to get to. It's just going to take us a second. We're going to look into it once they actually explain what it is, but they mention it twice, so they seem to be quite obsessed with this particular little architectural trick. All right. OpenELM architecture. The OpenELM architecture is a decoder-only transformer, and you're going to see this in all of these papers. So here in the Phi-3 technical report, they also mention that, right? So Phi-3 is a transformer decoder architecture. And what is decoder-only transformer? Like, what does that mean? So we have a pic for you guys here. This is the original diagram of a transformer architecture from the Attention is All You Need paper. And in the Attention is All You Need paper, I think what they were doing was translation. So they were basically trying to translate one sentence in a language to a different sentence to a different language, right? And in that type of problem formulation, they basically had an encoder in which you would feed your language in something like French, and then your decoder would output the English language sentence. So in that case, the encoder is encoding that French sentence into some kind of token or representation that is basically, this is the meaning of that French sentence. And then they have this cross attention here where basically you're feeding the compressed representation of that French sentence here into this attention that's allowing you to basically compare the English sentence as you're building it token by token autoregressively with the meaning of the original French sentence, and in that way get the English sentence. But we're not really doing this type of like translation task anymore. So pretty much anytime you're interacting with a modern language model, you're interacting with what's called a decoder only, which means they're only using this red part, right? So you basically have just your tokens coming in, and then you're predicting the token at the output, and then autoregressively getting the next token, and the next token, and the next token, and this is what's called a decoder only. So that's what they mean here with the decoder only transformer. But current decoder models can do translation well too. How? Basically, they do it the same way. If you do translation with decoder only transformer, you're basically feeding in the entire French sentence into here, and then whenever the English sentence is coming out of the top, token by token, it's just paying attention to the previous tokens in the sequence, which are in a self-attention, right? So rather than encoding the entire French sentence and then using that in a cross-attention way with what you're autoregressively outputting from the decoder, your French sentence is just the beginning part of the sequence, and then that part is just going through the self-attention as every other part of the sequence. Yeah, we just figured out that the decoder is all you need. Yeah, you don't really need this, because the problem with this is that you need to basically run this encoder first, right? So like you can't, in a decoder-only architecture, you can just immediately start outputting tokens, versus in here, you have to encode everything that you want and then use that in a cross-attention way. So it's just additional complexity that you don't really necessarily need, because the decoder-only works totally fine. Okay. A couple other tricks that they use. They do pre-normalization using RMS norm. So the pre-normalization means, you see here how this says add and norm here. So in the original transformer, the normalization was being done after the attention and after the feed forward, but now normalization is actually done before. So that's what the pre-normalization means. It means that you've moved these added norms up here to the front. And they also have a little trick here that they do with this normalization between RMS norm and layer norm, but we're going to get to that later. They use rotary position embeddings, rotary position embeddings. And they also use grouped query attention and flash attention. Grouped query attention, I have a little thing here. Grouped query attention is an interpolation of multi-query and multi-head attention that achieves quality close to multi-head at comparable speed to multi-query. So you see here a nice little diagram. Multi-head means that for every query, there is a corresponding key. So the dimensionality of the keys and the values in the queries, which are the core parts of that attention mechanism, are the same. In multi-query, you basically have a lot of queries, but only one key and value. And then grouped query is basically in between that. So because a lot of modern LLM architectures are doing this kind of KV caching, which allows you to more efficiently perform inference, having less keys and values in your KV cache is going to allow you to do things faster. So that's kind of why people are using grouped query attention. And in a similar kind of flavor, flash attention is also a way of kind of doing things faster by exploiting the way that memory is stored inside a computer, right? You have your CPU memory, you have your GPU memory, and then within the GPU, you have different levels of memory. And flash attention is basically being clever about that, about where you store different things on the GPU in order to more efficiently perform the attention mechanism, which is really the slowest part of a transformer. So they're using kind of all the basic tricks here. They use the same tokenizer as LLaMA, which Phi-3 also uses. So Phi-3 here, we're kind of skipping around, so I apologize if it gets a little bit confusing, but Phi-3 is also going to be using the LLaMA-2 tokenizer, which is a vocabulary size of 32,000. So when your language model is predicting tokens, right, it's basically picking which out of the 32,000 possible tokens is the best token to output. right? And you can have various different types of decoding strategies. You can either do greedy decoding, which is just picking the best one. You can do the fancy kind of MCTS type of decoding that we were looking at last week, where you're kind of doing a little bit of branching there, making a little tree, and then picking the particular path. But the important thing that I thought was worth noting here is that this isn't the good tokenizer anymore. So both OpenELM and Phi-3 use the LLaMA-2 tokenizer, which has a vocabulary size of 32,000, but LLaMA-3 actually has a new tokenizer. So LLaMA-2 has a tokenizer with 128,000 tokens now. So 128,000 tokens, which you have more nuance there, right? You have more possible tokens that can encode more possible kind of knowledge, right? There's more nuance there. You probably have more special tokens. You probably break up numbers and special characters a little bit better. So both of these are still using the old school tokenizer as opposed to the new tokenizer. Existing LLMs use the same configuration for each transformer layer in the model, resulting in a uniform allocation of parameters across layers, e.g. the number of heads and feed-forward network dimensions. So here they're talking about layer-wise scaling. So layer-wise scaling is the one trick that they kind of choose to highlight out of all the other tricks, right? In this paper, they could have really talked about any of these tricks, right? So none of these tricks are original to them. Layer-wise scaling is not something that they invented. This is something that I think is actually quite old at this point. It's like 2019, something like that, 2020. But for some reason, they chose to kind of explain what layer-wise scaling is. In layer-wise scaling, you're basically changing the dimensionality of the FFN and the number of heads in the multi-head attention. So what does that mean? We're going to pull up this. This is a visualization that I love to show. It's a visualization of a transformer architecture. You see you have your multi-head attention right here. And then you have your feed forward right here, or your MLP. And if you notice in this thing right here, right, there's the same amount of heads. Here you have 3 heads, right? There's your 3 separate heads. And if you go to the next block, you also have 3 heads. And if you go down to the last block here, you also have 3 heads, right? And if you look at the dimensionality of the FFN, it's the same dimensionality here. It's the same dimensionality here. And it's the same dimensionality here. So most transformers do this, right? It's always the same number of heads. It's always the same width of this FFN or multi-layer perceptron. In layer-wise scaling, you're going to basically adapt that. So as you're training this, you're going to basically change the width of that FFN, and you're also going to change the number of heads. So here they have alpha min, alpha max are the hyperparameters that allow us to scale the attention heads, and beta min, beta max let us to vary the width of the FFN layer. So in a layer-wise scaling, you're going to change the width, which is this right here, right? So the width of the FFN, and then you're also going to be changing the number of the heads. So depending on where you are in this, right, you're going to have a bunch of these transformer blocks all stacked on top of each other. Here you have 3. In layer-wise scaling, you're going to pick and choose, or slowly over time, kind of come to the correct amount of heads and the correct width for the FFN, depending on the layer, right? Because different layers are going to be dealing with a different higher, like the layers that are lower, right, are going to be kind of more in this lower level feature space. And then as you go higher and higher up into the transformer layers, you're dealing with a kind of more abstract, higher level feature space. So it makes sense that depending on where you are in that hierarchy of abstraction, you would use slightly different width and slightly different number of heads. So that is layer-wise scaling. Damn, all right. Looking up at the comments, you guys are already blasting. Mito. Question from Mito. Do you have any recommendations for a page where we can review the source code of the model architecture, or perhaps a portion of it? I mean, the code of the model itself, so like the actual model architecture, that's required for inference. So here, whenever they say the inference code, that's the actual model architecture, right? So you can actually go there and look at that, right? So we can go here on Apple. We can give them a little star. 3.7 stars is pretty good. What else? We go here, boom, 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 into CoreNet. There you go. Into blah, 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 blah. Where is it? Metrics, loss, engine. Maybe it's in here. Let's see. Engine, evaluation engine. No, that's probably not what we want. We want data metrics modeling. Maybe in here. Modeling. Layers. Here you go. Boom. go. Here's the dropout, embedding, the base layer. Here's your multi-head attention, linear. So all of the multi-head, like this is the source code, right? But what they were trying to say here is that that's not everything, right? A big part of deep learning is not, the model architecture is really just one piece of it, right? You kind of need to have all the training and evaluation code as well, right? And all the code that kind of filters the data set, picks the data set. There's so much other code than just the model architecture. So what they're advertising is that here, if you go, you can see, you can click train eval pipelines. Here's the actual default train eval pipeline that they used, right? So they're releasing their learning rate schedule, their data loaders, and you need those in order to actually fine-tune these models. So the model architecture only gets you so far. LLaMA-3 uses the same as GPT-4 as far as I can remember. Huh, that's interesting. So Work, you're saying that the LLaMA-3 tokenizer is actually the same as the GPT-4 tokenizer, which is pretty cool. I don't know if did GPT release the GPT-4 tokenizer? I know that they released the earlier tokenizer, but I don't know if they released the one that they actually used for GPT-4, but I don't know, maybe not, maybe yes. Okay. I tried to train a transformer model from scratch. This is a question from Muthu, but my PC is dead slow. Any recommendation in how to train on AWS or any instance with a low budget? Yeah, these type of models are going to be very difficult to train. You're not going to train a 7 billion transformer model on your GPU at home, right? These are trained on very large GPUs in the cloud. And even if you had, like, even if you wanted to do that and you went on the cloud and you wanted to train, like, you're not going to have the money. Like, these things are beyond kind of something that you can do at home, right? Like, all of these models at this point, like, you need millions of dollars to train these, and even if you're doing it on the cloud, right, you don't need to purchase your own GPUs. You're purchasing time and renting these GPUs on the cloud, but even then, it's still going to cost you a lot of money. So the best you can do at home is just take these models and fine-tune them a little bit on your specific use case. Okay. Is this paper also using the same group query attention, which is mentioned in the tech report of LLaMA-3? Probably. I think there's probably slightly, you see, for example, here in the Phi-3, they also use the grouped query attention. I'm not like deep into the grouped query attention implementation. I'm sure there's slightly different implementations of grouped query attention that have slightly different negatives and positives. So I'm not entirely sure whether Phi-3 and LLaMA-3 and OpenELM are all using the exact same implementation of grouped query attention. But, you know, at the end of the day, and this is something that we're going to come to a conclusion of in this stream, the architecture isn't super important, right? So it's not, don't worry too much about the model architecture. What we're starting to realize, and I'm maybe cutting to the chase here, is that the data set is really the most important part. So don't worry too much about it. All right. All right, and talking about the data, the pre-training data for OpenELM is going to be refined web, the pile, and Red Pajama, and Dolma v1.6 for a total of approximately 1.8 trillion tokens. All right, and here they have a nice little table where they basically show you what that is. So Red Pajama is a combination of GitHub and books and archive papers and Wikipedia. It's also, you have the pile, which I think is code. And you have, for example, Dolma is Reddit, more Wikipedia, more Project Gutenberg, whatever the fuck that is. I think that's just books. But the important thing here, and this is what they're not really telling us, right? So even though they said they're going to release more than other people, the one thing that they don't release, which is probably the most important, is this right here, subset. Subset. So subset means not the full Red Pajama, but a curated, smaller mix of Red Pajama, right? And that curation, taking Red Pajama and making a smaller version of it that is more curated and more clean, that's honestly the most important part. So we're going to see that that's kind of really what we wish they were releasing, is these subsets of the common crawl data sets that are available, right? Because data quality is very important. Unlike previous approaches that utilize pre-tokenized data, we filter and tokenize the data on the fly, experimentation with various tokenizers. So this is actually another interesting point here. A lot of times when you're training a model, right? For example, if you're training some kind of VLM on a data set of images, you'll pre-encode those images, right? So an image is a relatively large amount of data, right? It's just like this big array of pixel values, but a image representation is just a little vector, and it's a much smaller thing, right? So if you're going to be feeding batches of training data into your model, and that model is being trained in the cloud, you don't want to be passing images and back and forth between these cloud machines. It's a lot easier to just pass image encoding or image representations back and forth, right? They're a lot smaller. So a lot of times when you're training, you basically pre-encode your raw data into like a little vector that's a lot easier to pass around. And a similar kind of thing is happening with tokenization, where a lot of times when people train on these text data sets, they'll pre-tokenize the data, and then they'll train on that pre-tokenized data. But what that means is that now you're kind of stuck with the specific tokenizer that you're using. So if in your training and training scripts, the tokenization is done as you're consuming the data, then you can switch out the tokenizer and try different tokenizers as part of your hyperparameter sweeps. So if you're doing some kind of experiment paper like this, where you're trying out different things, trying out the tokenizer is probably a good idea. So doing your tokenization as you consume the data such that you can change it and have different tokenizers as one of your hyperparameters is a pretty good idea. It's worth the extra overhead. Okay. All right. They train for 350K iterations. We use Atom W as the optimizer. Nothing unusual there. You have improvement with increasing training duration. So here you have the different sizes of OpenELM. You have 3 billion, which is pretty small, and then 270 million, which is tiny, right? Like a LLaMA-3 is considered small. So a 270 million parameter OpenELM is absolutely tiny. And I think the reason these things are so small, and the fact that it's Apple, is that these are totally intended for cell phones, right? So I think that what they're trying to do here is train models that they will be able to deploy on a cell phone, such as an iPhone, right? So that's why they're kind of doing extremely small models, right? They're not trying to push the state of the art. They're not trying to make a LLM that's better than all the LLMs, because in that case, you would probably just try to make the size as big as possible, right? This one, they're really trying to get it to a point where they can run it on a cell phone. Okay, blah, blah, blah. We're going to kind of skip through some of these. We're going to go back to the tables once we've kind of looked at all the papers. Additionally, the checkpoint obtained by averaging the last 5 checkpoints demonstrates comparable or slightly better accuracy compared to the final checkpoint, likely due to noise reduction through weight averaging. So this is a nice little tip here, is that when you're training your model, right, you're training your model, here's a nice little curve here, right, you're training for 5,000 iterations, and then another 5,000 iterations, and then another 5,000 iterations. So every 5,000 iterations, you save your current model, right? So you're taking those weights and you're saying, okay, I'm going to save these, and that's going to be called a checkpoint, right? So over the course of your 350K iterations, every 5K iterations, you're going to have a checkpoint. The one that you actually use for inference, or basically the one that you release and that you want people to use, you're not going to necessarily use the last checkpoint. What you're going to actually do is you're going to pick the last 5 checkpoints, and those are each going to be a different set of weights, and then you're going to average those together, and then that is going to be your final model that you use for inference. And one way to think about why this works is that you're feeding batches of training data into your model. So the gradients that you push are based on the last batch of data. So if your last batch of data was a little bit weird, then the very last gradient push that those weights received might be a little bit weird as well, right? So like, in order to account for the kind of fact that the different batches of data that you're feeding into your model as you're training it have slightly different biases and are kind of maybe sampled a little bit weird, right? You don't really know what's going to end up in each batch. The average of the 5 last checkpoints is going to be more kind of general than each individual checkpoint itself, right? So I don't know, maybe that wasn't the greatest explanation, but the average of the last 5 checkpoints is going to be better than the individual last checkpoint. And that's a little tip for anybody training anything, really. All right. They do some instruction tuning, which is the second part of the process, right? You do your pre-training, and then you do your instruction tuning in order to turn it into an actual chatbot. Here they have a little bit of explanation about their hardware. So they fine-tuned the resulting model on 3 epochs using 8 NVIDIA H100s. So we're finally seeing papers start coming out where people are training on these H100s. Those, I think now obviously you have the better ones that have been announced by NVIDIA. I think that OpenAI even got their first H200, but this is the H100s, which is basically the best GPU that you have right now. And then you have a server rack that has 8 of these. So 8 NVIDIA H100s is probably the pinnacle of what you can train on right now, but soon it'll be eclipsed by the H200s. And then in terms of running this model, so this is what they use for training, but then they want to actually test how this will look in inference. So for inference, they're going to train on what they can kind of consumer grade, or they're not going to train, but they're going to perform inference on a consumer grade setup. So this is what they assume that the random person on the internet is using, and they have here an Intel CPU with 64 gigabytes of CPU RAM, right? So if we go back to our this CPU DRAM right here, this is the kind of the lowest level of memory, right? And this stuff is actually kind of annoying because you have to, if you put anything in this memory, you have to move it into the GPU memory. So that's this 64 gigabyte of DDR5 DRAM. Then they have an NVIDIA RTX 4090 with 24 gigabytes of VRAM. So the NVIDIA RTX 4090 is going to be this part here. So that 24 gigs of VRAM is actually going to be split. There's going to be some part of it that's SRAM, some part of it that's this HBM, high bandwidth memory here. But if I know I get this question all the time, right? I feel like every machine learning Discord that I am part of, one of the most common questions that people have is like, hey, I'm trying to build a deep learning computer at home. Like, what do I need to do? And here it is. So if you want recommendations for hardware and your operating system, such as Ubuntu, here's a good little recommendation for you directly from Apple themselves. So they think that this is kind of like an example of what a consumer would be using, an open source person. So you can copy their setup. And then, of course, they want to perform inference on an Apple hardware. So here, this is indicative of what Apple hardware you could use to perform inference with this model. The Apple MacBook Pro with an M2 Max system on chip, 64 gigabytes of RAM, running Mac OS 14. We ported the code and weights of OpenELM to Apple MLX. So obviously, if you want to run it on Apple, I don't know if you use PyTorch, but you definitely want to use MLX. Okay. Evaluation. 2 separate measurements for token throughput, prompt processing, and token generation. We warm up the model by executing a single forward pass to allow any frameworks to perform further auto-tuning. Okay. What else? We did comprehensive profiling to understand the bottlenecks. Okay. Our analysis reveals that a significant portion of OpenELM's processing time can be attributed to our naive implementation of RMS norm. This results in many individual kernel launches, each of which processes a small input rather than the launch of a single fused kernel, as would have been the case with layer norm. Okay, so what are they talking about here, right? Fused kernels, RMS norm, layer norm, like what is going on? So as we mentioned before, normalization is this part right here, right? Your normalization, and that used to be done afterwards, but now it's done before, so it's pre-normalization. But then there's also a lot of different types of normalization. So here I have something that just kind of tells you what is normalization. Normalization is taking your data, which might be like this, unnormalized. You see how all of these values kind of look the same. And whenever we normalize them, we basically spread them out or shape them nicely. But really what you're doing is you're almost like, think about it like you're pinching on your cell phone and you're zooming in like that, and you're making it so that your data now, rather than being between 0 and whatever this is, 20, some arbitrary numbers, you're making it between 0 and 1, right? So that it's very easy to tell the difference between the data, right? So you can tell this data point 0, this data point is 1. So it becomes easier for your model to actually consume that and tell the difference between different data points, versus if you don't normalize them, all of them might look the same and it's just not going to learn nicely, right? So you want to help your model learn, and normalization allows you to do that. There's a lot of different types of normalization because you basically choose along which dimensions you're normalizing, right? So you have batch normalization. It's going to normalize on the batch. So every time you're feeding a batch of data, you're normalizing within that batch. Layer normalization is saying, okay, everything that's going into this layer, so in each individual layer in a deep learning model, we're going to normalize along that dimension. Instance normalization, group normalization, a lot of different types of normalization, right? But an RMS norm, let me see up here, I have a GitHub comment. This is a GitHub comment where they're talking about this fused RMS norm. Here's the exact equation for layer norm versus RMS norm. It actually turns out that RMS norm can be layer norm. It just has a couple different differences, but they're very similar. But the core thing that Apple is talking about here is that they have a naive implementation of RMS norm, and they want, and the reason it's slower than layer norm is because the layer norm that they used is a single fused kernel. And what does that mean? Okay, so if we go back to here, into this flash attention, part of what flash attention does is it takes these kernels here. So in your attention operation, right, your attention equation, you're going to be doing a couple operations. You're going to be doing some matrix multiplication, then you have some dropout, then you have to feed that through your activation function, or you're going to have to feed that through the softmax, right? If we actually look at the attention equation, this one right here, right? So you have this softmax. Here's your matrix multiply. So your Q times your K, that's your little matrix multiply right there, right? Then you have your softmax. You have another matrix multiply. Each of these is a kernel, and a kernel is basically the actual operation that runs on your GPU, right? So that's what's actually running on your GPU, your kernel. So whenever you write your Python code, it's being compiled into this kernel, which is then, that's what's actually running on the GPU. If the idea of fusing is basically saying, okay, well, actually all these operations here, right, there's actually a way to do them all at the same time, and that's what's called a fused kernel, right? And fusing a kernel is going to make it much, much faster than doing each of these independently, right? So time in milliseconds to compute all of these operations here, and you have to wait for this one to finish before you can do this one, and you have to wait for this one to finish before you can do this one, you have to wait for this one to finish before you can do this one. If you can fuse those, you can drastically improve the speed and performance, not performance on benchmarks. In terms of performance on benchmarks, it's going to be the same because this is going to be basically mathematically equivalent to this. But that's the idea of a fused kernel, right? And you need to do this for kind of every op that you can, and there's a lot of opportunities to do this. And just to kind of show you guys what this looks like, here is a issue on the TinyGrad. TinyGrad is basically, you could think of it like an open source PyTorch. I guess PyTorch is kind of open source anyways, but it's a re-implementation of PyTorch led by George Hotz. And in here, he has a $2,000 bounty to create a fused norm, right? So he's running into the same problem that Apple is running to here, where, hey, we're using RMS norm, but we're using a version that isn't fused. We'd love to have a fused, single fused kernel version of RMS norm. There you go. That's exactly what GeoHotz is saying here. He's saying kernels 8, 9, 10, and 11 should be fused into one, right? So he's basically saying this kernel here, so you can think of the 0, 1, 2, 3, 4, 5, 6, 7. Think of that as basically this, right? You have all your kernels, 0, 1, 2, 3, 4. And he's saying, hey, actually, 8, 9, 10, 11, those, you can probably fuse them into one kernel, and then that'll be way faster. So in Apple or PyTorch's case, you probably have to either do it yourself with your own engineers or wait for some other person to do it, or if you're George Hotz, you can just put out a $2,000 bounty, and it looks like someone actually did it. So it looks like Woe's Parrot actually implemented that. And this stuff is very difficult to do, right? So like writing fused kernels like this, you have to be able to think in like very high dimensional spaces, and you have to know like the ins and outs of CUDA and GPUs. So very difficult to do, but that is what fusing kernels is, and why layer norm is a little bit faster than RMS norm right now, even though they're kind of very similar. Can you give a gist of how it's fused mathematically? I mean, the fusion is going to really be on a case-by-case basis, right? That's why this stuff is complicated, right? If fusing kernels together was something that you could just kind of heuristically define, then it would just be part of the compiler, right? So like the fact that you have to create these fused kernels kind of yourself as a human, you have to sit in there and think about how you would fuse this together. That is why you need someone to do this. You need an actual human to do this. If you could just do this automatically and there was like a simple equation that allowed you to say, okay, here's how you can fuse 4 kernels into 1 kernel, then people wouldn't need to do this type of fusing. You wouldn't have these bounties. You wouldn't have these issues here. Okay. Let's keep going. All right, I think that's pretty much it for this paper. Let's scroll over here. We're going to bounce around too, so don't worry too much about losing track of where we are at. All right, Phi-3 technical report. This is Microsoft's small open source language model. They introduced Phi-3 Mini, 3.8 billion parameters, so very similar to the size here, right? This one has 1 billion, so 3 billion is kind of on par, right? These are cell phone models. That's why they're that small. It's trained on 3.3 trillion tokens, so 3 times what this one is trained on, right? This is trained on, or not 3 times, this one's kind of 2 trillion. So OpenELM is trained on 1.8 trillion. Phi-3 Mini is trained on 3.3 trillion. And then we know that LLaMA-3 has been trained on 15 trillion, right? So that kind of gives you a sense of the scale there about what these different training data sets in terms of size are. But the big thing about this Phi-3 paper, and it's also a storyline with this LLaMA-3, is heavily filtered data and synthetic data. Yeah, as Kalina says, it's mathematically equivalent, right? So the whole point is that this fused kernel here is doing the same exact thing that these kernels here are doing. Yeah, reduces memory transfer. Think about it. Here's like a very naive way of thinking about it. Let's do text. Like this is an extremely, this is not 100%, this is not correct, but like think about it this way. If you were doing x plus equals 5, x plus equals 6, x times equals 4, right? Like that would be unfused. Let me make this a little bit bigger. Fused would be something like this. X equals 4 times x plus 4 plus 5 plus 6. So obviously this doesn't mean shit, because like in any programming language, this would be like behind the scenes, this would all be kind of done for you. But this is kind of the main idea, right? If you want some high level intuition about what fused kernels are, it's basically that. Right? You're basically just doing it all at the same time, but it's mathematically equivalent. Okay. Back to here. Heavily filtered and synthetic data. Okay, this is what we wanted to talk about. The impetus for this effort originates in the seemingly predictable improvement from so-called scaling laws. However, these laws assume a fixed data source. And in this case, they're going to use a combination of LLM-based filtering of web data and LLM-created synthetic data to enable performance in smaller large language models that were typically only seen in much larger models. Okay, so what they're talking about here is that for most of the lifetime of deep learning, we were operating in a kind of academic environment. And in that academic environment, usually the data was fixed, right? So usually you had something like MNIST or ImageNet, and you basically, the different papers were all using ImageNet, and then they were keeping the data fixed and then changing the model architecture, right? So if you keep the data set the same and you try out different model architectures, certain model architectures are going to perform slightly better. But there's a misleading element there where you're assuming that the model architecture is what's driving performance. But that's not actually the case, right? Really, it's the data set that's driving the performance, and the model architecture is not really that important, right? And to kind of drive this point home, I have, where is it? Right here. So this is a little blurb that someone from OpenAI wrote, and this is, I've been at OpenAI for almost a year. In that time, I've trained a lot of models, more than anyone has really the right to train. As I have spent these hours observing the effects of tweaking various model configurations and hyperparameters, one thing that has struck me is the similarity in between all the training runs. It's become awfully clear to me that these models are truly approximating their datasets to an incredible degree. That means that not only are they learning to do blah, 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 what this manifests is that trained on the same dataset for long enough, pretty much every model with enough weights and training time converges to the same point. It implies that model behavior is not determined by the architecture, hyperparameters, or optimizer choices. It's determined by your dataset, nothing else. Everything means is an end in efficiently delivering compute to an approximate a dataset. Okay. When you refer to Lambda, ChatGPT, Bard, or Claude, it's not the model weights, it's the dataset. And this is a little bit of a simple take, right? Like, there's obviously some effect of the model architecture, but I agree with kind of the kernel of truth in that take, that the dataset is really the most important part. And because of the kind of academic history and academic origin of deep learning, we were always using these fixed data sources, which kind of gave us the wrong intuition that model architecture and kind of the different tricks that you're using for training are what matter, when in reality, it's the data set that matters. And if it's the data set that matters, then really what you should be doing is figuring out the subset of red pajama that is more worth it, or creating a synthetic data set that allows you to train better, right? So it's like really the data set creation, the data set curation, the data set filtering, that's what really matters. And the model architecture is kind of like a red herring. Okay. Phi-3 Mini is a transformer decoder, context length of 4K. We introduce a longer context via long rope. We actually have a stream on that, so if you're interested in long rope and context length extension, check out the stream for that. Uses the LLaMA-2 tokenizer, vocabulary size of 32,000, which we saw that the LLaMA-3 tokenizer now has 120,000, so already outdated. They trained using bfloat16, and bfloat16 is going to be a good introduction here to quantization and data type. So because they want this model to run on a cell phone, they're going to be doing what's called quantization, and they're going to be quantizing to 4 bits so that it only occupies around 1.8 gigabytes of memory. So what is quantization? And I'm going to pull up a image that I kind of show all the time. Let's see if I can find it. This one here, this one here, this one here. Okay, so any number that you have on your computer is being represented by some amount of bits, right? So your computer has a limited amount of little storage places, and the precision of the number is going to depend on how many of these little storage spaces you're using, right? So data types are different ways that you can represent a number. So a floating point 16 is using 16 of these little bins to store your number, right? And it's using one bin to store the sign, whether it's negative or positive. It's using these little green bins here to store the exponent. So whether it's 0.1 or 0.00001 or 0.0000001, right? The number of zeros before or after, that's going to be the exponent. And then this is the actual number here, the mantissa, right? So you can see how there's different data types here, and you can see how, for example, bfloat16, which comes from brainfloat16, which comes from Google Brain, it's a variant of a floating point 16 that has more of these exponents. So you can have 0.0000001, right? You can have very, very small numbers, very, very big numbers. All right. But the important part here is to look at these ones here. So you have int8 and int4. So if you have a model here, when they're saying quantizing to 4 bits, right, what they're basically saying is that every single number, every single parameter in this model, right, of which there's 3.3, what is it, 3.3 billion or 3.8 billion parameters, every single one of those numbers is being stored as a bfloat16 when you're training. So think about how much memory it takes, Jesus Christ, how much memory it takes to store 3.3 billion of these numbers, right? And now be like, okay, well, if we could instead store all of those numbers as int4s, right, 4 bits, we're saving ourselves a hell of a lot of memory, right? Like it's whatever that is, 1/4 the total amount of memory to store everything in 4 bits as opposed to 16 bits. So that's one way to take a model that's relatively big and then make it way smaller. And you're making it smaller, you're also making it faster. And in this case, they want to do that so that they can deploy it on an iPhone 14 with an A16 Bionic chip. And you get about 12 tokens per second. Can you talk about 1-bit LLMs in the context of quantization? Yeah, 1-bit LLMs are basically the extreme version of that. And you can think of it like it's basically storing each model weight in 1 bit, but it's usually not 1 bit, right? Because you're not... So there's a lot of different types of quantization, and actually in this paper here, which we're going to get into, they try out a bunch of different quantization techniques. So this is a paper on LLaMA-3, where they study quantized LLaMA-3. I called it QLLaMA-3 just because I wanted the title to fit, but QLLaMA-3 doesn't mean anything. QLLaMA-3 is just my abbreviated form of quantized LLaMA-3. And in this paper, they compare all the different types of quantization. So quantization is not just the number of bits that you're using to store those parameters. It's kind of like how you do that. And there's a bunch of different techniques for that. So for example, RTN, AWQ, Smooth Quant, BiLLM, PTQ, QLoRa, IRQLoRa, LoRa-FT. All of these are different types of quantization techniques. They all have their own little tricks. And here in this paper, they compare all the different types. So they're like, okay, the original LLaMA-3, which is in 16 bits, this is the score that it gets. Okay, here's using GPTQ, which we compress GPTQ with 8 bits, you get this, right? Which is pretty good. Look at that. LLaMA-3 16, 68. GPTQ 8, which is half the size, 68. So, okay, you're not losing any performance. But GPTQ quantized down to 2 bits, 34. So you can see here, this is the problem with quantization, is that when you reduce the precision of the number by quantizing it or sticking it in a lower data type like this, you're losing some of the information, right? So it's like you're making the model a little bit shittier, right? So sometimes it's fine, right? So like here you see 4-bit 64. So like 64 is really not that much worse than 68, and 4 bits is 1/4 the size of 16. So losing 4 percentage points for a model that is 1/4 the size, totally worth it, right? But going down to 2 bits, now you're losing almost 30 percentage points. So that's not worth it, right? So there's kind of like a weird... There's a point at which you quantize too much and your model kind of becomes worthless. But different techniques are potentially going to be good or bad. So I think that, for example, here, BiLLM, just to finally get to your answer about 1 bit. So work here is an example of BiLLM. You see that none of them are really, they're never really truly 1 bit because they're usually not compressing every single parameter in the model to 1 bit. Usually there's other parameters that they keep at a higher precision. So 1.1 means that basically the average number of bits that's being used to store all 3.3 billion, 3.8 billion parameters ends up being around 1.1 bits. So you can see here 37, 36. None of these are amazing, right? You're really not getting a 1 bit or close to 1 bit quantized version of the LLaMA that is at the same level as this 16-bit LLaMA right here, right? But you're getting some of them that are kind of close here. So here, for example, DBLLM, 2 bits, 51. Like now we're talking, okay, 51 for 2 bits, that's pretty good. How's it going, Timothy? Do I know which quantization method is used in BNB? No. There's a lot of different quantization methods, right? So it's not, quantization is not like a fully understood science yet. It's alchemy, right? You're just trying weird shit. There's like 50 different types of different tricks that you can use, and all these different types of quantization are using some subset of all the available tricks, and some of them work well, but only some of them might work well for some situations, some of them might work well for other situations. And with anything deep learning, as I said, it's alchemy in that you don't really know. You just kind of have to try out a bunch of things, experiment, and then figure out the things that work. Okay. I think that's pretty much it. Let's go back. So they're quantizing this. Our training data consists of heavily filtered web data, synthetic LLM generated data, and synthetic data is really becoming a go-to thing, right? We saw in Zuck's interview with Dwakesh, who's like this podcaster. He talked about this. He talked about how when they were training LLaMA-3, they also had synthetic data that was being generated by the model in order to feed that, in order to train on that data. So we're starting to see basically this self-play loop, right? And if you go to some of our previous videos, such as the Q-star video, we talk about this, how in reinforcement learning, usually you're collecting experience or you're collecting data from your policy and then using that collected data to further train your policy, right? So there's this idea of like the model creates the data that it trains on, right? So that is starting to leak into the language world as well, where most of these language models that you're seeing now are using some form of self-play or synthetic generation in order to create the data that they're going to get trained on, right? The usually synthetic data is limited to things like math or coding or some kind of domain where you can verify the validity of that data, where you can say, okay, here's some generated Python code. Let's actually make sure that it works. And then if it works, then we'll train on it. But I suspect that some of the more advanced labs, such as OpenAI, and this is the kind of conspiracy theory around Q-star, is that Q-star is really OpenAI figured out how to synthetically generate data that is more general than just like math and code, which means you get a self-play loop that basically you could infinitely run. Okay, yeah, this is the other thing I wanted to talk about, which I thought was interesting in this paper. So one of the more interesting kind of little tidbits in this paper is this part here. Mostly of web sources aimed at teaching the model, so they train in two different phases. So they're, as I said before, training is kind of becoming complicated. You're having these kind of like multi-step, the way I say it is kind of like a training curriculum. So your training curriculum is like, what things are you training on and in what order? And here they have a two-phase training curriculum here. And the first part of it, you're teaching the model general knowledge. And then phase two, you have heavily filtered web data with some synthetic data. So whenever you're training on stuff, if you train on one thing and then you train on another thing, you have this problem that's called catastrophic forgetting, where basically when you train on the second thing, you're going to start forgetting the first thing that you're training on. So what you want to do is when you're training on the second thing, you put a little bit of the stuff that you had in the first thing such that it doesn't forget the first thing. So in the beginning, they're just training on web data. And then in phase two, they're going to be training on their synthetic data. But if they only trained on pure synthetic data in phase two, it would kind of forget the original phase one. So the phase two is not just going to be synthetic data, it's going to be that synthetic data, but mixed with some of the phase one data. And specifically a heavily filtered subset of the phase one data. And how is that filtering being done? And the filtering is being done such that the web data contains the correct level of knowledge. Okay, we keep more web pages that could potentially improve the reasoning ability for the model. As an example, the result of a game in a Premier League in a particular day might be good training data for frontier models, but we need to remove such information to leave more model capacity for reasoning for the mini-size models. Okay, I think they have one more sentence here. There's one more sentence here that I want to read before we go. Yeah, the model simply does not have the capacity to store too much factual knowledge. Such weakness can be resolved by augmentation with a search engine. Okay, so this is really, really cool. And here I'm going to tell you why it's cool. A lot of the time, when people train these, right, they were just training on web data. But a lot of that web data is kind of like facts, right? It's like, okay, and this particular day, this soccer match happened and this score happened, right? And when you're you're getting your model to learn from that data, what you're telling it is just to memorize a bunch of these facts, right? But you don't actually care about those facts, right? What you really want is for the model, the language model, to have a reasoning ability. You want it to have the ability to kind of like reason about things and perform logic, and kind of, that's what you want it to be good at, right? You want it to be smart in the way that it's like, it can reason through things and it can figure things out, rather than just being smart in the sense that it's just memorized a bunch of data. Because in the long term, you're going to be able to connect this model to a search engine, right? So we know that the way that this is moving, you're going to have basically a language model that has a bunch of tools that it can use, right? So it can use an external search engine as a tool, right? So the model can say, okay, I don't actually know what the birth date of Obama is, right? I was never trained on like the year that Obama was born, but I can find that fact very easily by using an external tool such as a search engine. If you assume that all these models are going to have access to external tools, then what we need to start doing is filtering all these little factoids from our training data sets. So that's probably what they did here as well, right? I bet you that Apple, in their OpenELM paper, came to the same conclusion that, like, hey, if you're going to be running this model on a cell phone, the model that's actually running on your cell phone just needs to be smart. It doesn't need to know a bunch of facts. So if it doesn't need to know a bunch of facts, why don't we go through all these data sets that have been crawled from the internet and just remove all the like unnecessary factoids and just only keep the parts that are kind of like making you good at reasoning and logic. And I thought, like, even though it's kind of like a throwaway sentence here, I feel like this is actually has big implications, because it means that we can, one, we should be filtering our data sets such that we only have kind of like reasoning type things. But two, these type of reasoning type data sets, those are exactly the type of data sets that you can synthetically generate, right? So you can't synthetically generate a data set of like people and birthdays, because those birthdays are made up, right? It's like you don't, synthetically generating factoids is not something that you can kind of validate, I guess. But generating this kind of reasoning data is much more possible. So in the future, we might have kind of a very clear distinction between a language model that's just used for, that just is very smart and good at reasoning and logic, versus like hard data, which is more just fixed in some database, and that the model just looks up that data. So I don't know. I just thought that that kind of distinction is interesting. Damn, you guys are popping off here. It doesn't need to remember facts, but think reasoning has an inherent idea of facts. What BF16 does is a very simple trick compared to quantization schemes. Quantization schemes tend to be more adaptive to the actual weight values. Yeah, that's true. There's a lot of complexity in quantization schemes. We've read a bunch of quantization papers on this channel, so like if you're interested in that, definitely check out all those streams. But my TLDR there is, it's kind of like this, you know? It's kind of the same conclusion here, where like quantization falls into this bucket here, right? It's like there's a bunch of shit that you think matters but doesn't actually really matter, right? And people are still trying to figure out what the best way to quantize is, but it might just be exploration in this particular hyperparameter space that isn't necessarily useful to explore. Okay, so post this training, which is a two-phase process, then they're going to do their instruction tuning. Their instruction tuning is going to use your standard SFT or DPO. SFT leverages highly curated data such as math, coding, reasoning, conversation, model identity, and safety. SFT starts with English only. DPO covers chat, reasoning, and responsible AI. So this is where they make your language model output the, I'm sorry, but as an AI language model, this is where that comes from, right? It comes from the fact that the very last batches of data that you're feeding and the very last gradients of gradients that you're pushing into those weights are coming from these safety data sets, these chat format data sets. So that's where you get all the cringe model behavior from. Long context extension is done in 2 stages. Okay, so we saw that's another popular kind of thing. Few shot prompts to evaluate the model at temperature 0. So this is how they actually get their scores. All right. So we can actually compare some of these. So MMLU, Phi-3, let's do the big one here. We get a 78. Let's go up to this. They don't have, here we go, MMLU, OpenELM. OpenELM 3.4. So the biggest OpenELM is at an MMLU of 26. Not looking good. Maybe this one is the one we should compare against. Okay, Phi-3 Mini, MMLU 68, but this is also 5-shot versus this one here is 0-shot, 3-bill, 26. This is why these benchmarks are like fucking not comparable, is because 0-shot versus 5-shot matters a lot. Let's see. Let's see if we can find one that's 0-shot. GSM 8K, 0-shot, but even this one is not 0-shot. It also has chain of thought. And they get the Phi-3 Mini, which is 3.8, gets a score of 82. Let's go to here. OpenELM. Do they have GSM? No, they don't. Okay, which one do they have? WinowGuard. Do they have WinowGuard? Here we go. WinowGuard. Unfortunately, it's 5-shot. Let's see. Pika. ArcC. ArcC. 10-shot. Jesus Christ. We need a 0-shot ArcC. Okay, we can't even directly compare these guys. That's the level of like reproducibility that we're at, where even looking at the tables, you can't directly compare. Okay. Let's go here. Quantized LLaMA-3, University of Hong Kong, ETH Zurich, Beihang University. And actually, I want to call out Yannick. So Yannick is another machine learning YouTuber, and he had a video recently where he made a very good point. And he made a point that as soon as LLaMA-3 came out, you suddenly had all these papers that came out immediately, right? And it's a little bit unusual, right? Like how can you like suddenly have a paper when this model just came out like a couple days ago? And the answer to that is that these guys are waiting on the releases, right? And there's an interesting dynamic here that props to Yannick for seeing this, but a lot of these academic groups, what they're doing is they're basically waiting. They have all this shit prepared, right? So this is a benchmark paper, which means that they have all the evaluation data sets ready to go. They have the paper pretty much already written, and the only thing that they're waiting on is for that model to release. And as soon as that model releases, they can just, boom, plug it in and then run all their experiments on it and then publish the paper. And because they already do have all the work ready to go, they can really, really quickly publish a paper. And if you're one of the first papers to be published for LLaMA-3 quantization, people are going to be looking at your paper, right? Exactly what I'm doing now, right? So I went and I picked this paper because it was one of the few papers available for LLaMA-3 quantization, and because it's one of the first papers available for LLaMA-3 quantization. So there's an interesting dynamic here that's happening where basically people are waiting for these open source model releases because they know that LLaMA-3 is going to come out. They know that LLaMA-4 is going to come out, and you have all your experiment infrastructure just ready to go, and you probably have the paper mostly written. And then as soon as the LLaMA-3 comes out, you can run your stuff, plug in those numbers, put those charts out, and put the paper on archive. So there's like a weird kind of like race that happens now anytime an open source model is released. Yeah. Okay. LLaMA-3 models have recently been trained. 15 trillion tokens of data, which again, pretty hardcore, right? 3.3 trillion tokens for Phi-3 Mini and 1.5 trillion tokens for this one. We don't actually know how much of this 15 trillion tokens of data that LLaMA-3 trained on, how much of that was synthetic, how much of that was curated such that you remove these little factoids like we were seeing here in the Phi-3, right? I'd love to know what the data mix is for LLaMA-3. Okay, but in this paper, they're basically going to explore the different low-bit quantization schemes that you can use. They evaluate 10 existing post-training quantization and LoRa fine-tuning methods, everywhere from 1 to 8 bits, using diverse datasets, and comprehensively reveal LLaMA-3's low-bit quantization performance. LLaMA-3 still suffers non-negligent degradation in these scenarios, especially in the ultra-low bit width. So LLaMA-3, if you quantize it all the way to 1 bit, it's going to be kind of shit. This highlights the significant performance gap under low bit width. Okay. Blah, blah, blah. LLaMA-3 models have achieved state-of-the-art performance, establishing the LLaMA family as among the finest open-source LLMs available. I would agree with that. LLaMA-3 is definitely kind of the king open-source model right now. Low-bit quantization reduces the memory and computation requirements during inference, enabling them to run on resource-limited devices, which is why Phi-3 quantizes to 4 bits so they can run it on an iPhone 14. Post-training quantization, PTQ, LoRa fine-tuning quantization, LoRa FT. Post-training quantization means that you're quantizing the model after it's been trained. All right, so you're taking that final weight file that people are giving you, which itself is a average of the last 5 checkpoints, right? So the last 5 checkpoints get averaged, and that's the final inference model, but the final inference is at bfloat 16, and then in post-training quantization, you're basically just taking that and then quantizing each of those numbers. LoRa fine-tuning quantization, this is a slightly more advanced type of quantization. So you see here, there's a couple variants of that, QLoRa, IRQLoRa, LoRa FT. So here's a nice blog post, I guess, but what is LoRa? LoRa is low rank, and here's a little explanation of LoRa. Here's LoRa in 10 seconds, or probably more like 30 seconds. So in your model, you have your weights, which are your parameters, and your weights basically multiplied by your inputs. You run your ops, you run your fused kernel ops, and then you get your output, right? Whenever you feed a batch of data in, you're going to have some loss function. That loss function is going to allow you to determine a gradient. That gradient is effectively going to be like a little update, right? So you're basically saying, okay, here's all the little changes to each of the weights or each of my parameters. And then you basically apply those. So then your weights change a little bit, and that's your updated weight. So this is effectively what you're doing when you're training a deep learning model. You're changing the weights a little bit every single time you perform a training iteration, right? So whenever they say here 350,000 iterations, what they mean is that they changed the weights 350,000 times. Whenever you're fine-tuning, you're doing the same thing. You're basically using batches of your fine-tuning data set, and then you're updating these weights, right? But if you're doing this in the vanilla way, every single one of these weight updates, all the gradients, the weights themselves, it's all being stored in floating point bfloat 16, which is quite heavy, right? So fine-tuning at full BF16 precision, very difficult to do because you need a very big amount of GPU memory because you need to store all of these weight updates and all of these weights in bfloat 16. So people have come up with a new technique, which they call LoRa, and we have streams on this as well. And in LoRa, you're doing the same thing, right? You're basically training, but you're not going to be updating the weights themselves. You're going to be updating this low rank adapter here, this LoRa. And this is usually how it's shown. So most LoRa visualizations show you this kind of WB, WA that look like little trapezoids, but this doesn't really, I think there's something missing here, and this is what it's missing. So this picture shows you why LoRa is better and faster and consumes less memory, is because in LoRa, you have these two matrices, A and B, and this A and B matrix are much smaller, right? And because of the way that matrix multiplication works, right? In matrix multiplication, the dimensionality of the output matrix is based on the leading dimension of the first thing and the last dimension of the last thing, right? So you're basically, it doesn't matter that the r is very small. So you d by r times d by r times r by k, you end up getting with d by k, which is the same dimensionality as the original weight matrix, but this here is a whole lot less weights, right? So that's what LoRa is. You're basically training these small matrices that allow you to change the behavior or fine-tune the behavior of the original model without actually changing the original model and using a lot less weights. So why am I talking about this? Is because a trick that people figured out is that you can quantize a model and then you can LoRa fine-tune that model that has been quantized and make up for some of the performance gap, right? So when you quantize your model, it kind of turns to shit, as we saw here, right? When you quantize your model, it kind of becomes a little shitty. But if you then take that quantized model and you LoRa fine-tune it, you can make up for some of that shittiness, right? So for example here, Q LoRa at 4 bits gets an average of 64. If we go up here, I guess that's about the same as GPTQ, but it's a way to kind of make up some of the performance, right? And that's why people use these LoRa techniques with quantization together, right? Their powers together combined. Isn't LoRa better so that there's no catastrophic forgetting happening? I mean, not necessarily. LoRa and catastrophic forgetting are separate things, right? You can catastrophically forget using LoRa. If you had a massive LoRa fine-tuning data set and then you train that for a very, very long time, the model would lose knowledge of some of the original. It would still catastrophically forget some of the original things. So catastrophic forgetting is more a function of like the relative size between your pre-training data set and your fine-tuning data set and how similar they are and how long you're training each for, right? So if you have a really, really big fine-tuning data set and a really, really small pre-training data set and they're not at all the same thing, you're going to catastrophically forget. If you have a relatively small fine-tuning data set and a really, really big pre-training data set and your fine-tuning data set is really not that different from your pre-training data set, you're not going to catastrophically forget. So catastrophic forgetting is more has to do with the data sets rather than necessarily whether you're using LoRa or whether you're pushing gradients directly into the weights or so on. Okay. Okay, but there was one thing that I wanted to talk about here, which they talk about, which is interesting. Okay. Various LoRa FT quantization methods obtain worse performance under quantized LLaMA-3 compared with their 4-bit counterparts, which is in stark contrast to similar phenomena on LLaMA-1 and LLaMA-2. So in LLaMA-1 and LLaMA-2, you were able to do this LoRa trick, right? You were able to quantize it heavily and then use LoRa fine-tuning to easily surpass the original floating point 16 counterpart. So if you were using Q LoRa and LoRa FT with a LLaMA-1 and LLaMA-2, you could get a 4-bit LLaMA-2 and a 4-bit LLaMA-1 to beat the floating point 16 one, even though you quantized it because you're using LoRa afterwards. That's not the case with LLaMA-3. So there's a new kind of phenomenon here, which is that LLaMA-3 has strong performance brought by its massive prescale training. So they're saying, okay, LLaMA-3 was trained on 15 trillion tokens. That's a lot of tokens, which means that the performance loss from the original model's quantization cannot be compensated for by fine-tuning on a tiny data set with low-rank parameters. Despite the significant drop from quantization that cannot be compensated by fine-tuning, 4-bit LoRa FT quantized LLaMA-3B significantly outperforms LLaMA-1 7B and LLaMA-2 7B. So LLaMA-3, a quantized LLaMA-3 is still going to beat a quantized LLaMA-2, but a quantized LLaMA-3 with LoRa fine-tuning is not going to be as good as the 16-bit LLaMA-3, even though in a quantized LLaMA-2 with LoRa fine-tuning would be better than a LLaMA-2 at 16-bit. So the narrative around using LoRa FT to make up for the loss of performance that you were getting with quantization is basically broken now. It seems that these new models, such as LLaMA-3, that have a small capacity but are trained for a very, very long time on a large amount of tokens, it doesn't seem like they're as robust. I don't know if robust is the right word, but they're a little bit more fragile, right? So what I mean by fragile is that if you quantize them, they're going to go to shit a little bit faster than the LLaMA-2s and the LLaMA-1s, right? The LLaMA-1s and the LLaMA-2s, the way that I think about it is like they were bigger capacity with respect to the data set, so you could mess with them more, right? You can prune them, you can sparsify them, you can quantize them, and they're still going to be kind of okay, especially if you LoRa fine-tune them afterwards. But it seems like that paradigm is becoming less and less of a thing, and these more modern models, if you try to fine-tune them or if you try to quantize them, they're a little bit more fragile and less capable of surviving these type of surgeries. Don't forget that the LoRa init principle single value and singular vector adaptation over Gaussian. Okay. I don't exactly know what you mean there. Okay. We evaluate the performance of LLaMA-3 across a variety of low-bit quantization. While LLaMA-3 still demonstrates superior performance after quantization, the performance degradation associated with the quantization is significant. I think that's pretty much it. Here's that Tim Detmer's paper, dude. This guy's the quant god. I've never met this guy, so like at some point, I feel like I'm going to run into this Tim Detmer's guy at a conference, and he's going to be like, dude, why the fuck are you talking about me? I don't even know you. But, okay, we'll leave it at that. Tim, okay, what Tim is talking about is the way that these A matrices are initialized. So you need to initialize these A and B matrices before you push gradients into them. Seems like the full FP16 range has caught up with the huge data of 15T. Yeah, I mean, it's interesting because there's going to be like a push and pull there, right? I think if you asked me 6 months ago, it's like my intuition was that quantization works very well, and ultimately we're going to be running heavily quantized models. So 6 months ago, I thought that the way this was going to look is that we're going to basically quantize everything. And anytime you're running a model on your cell phone, or even if you're running a model in the cloud, it's a heavily quantized model with some fine tuning or special tricks in there to basically make up for that little bit of loss that you get from quantization. But my intuition around that has changed, right? Because now I'm looking at what these guys are saying, and it seems like quantization is a little bit, it's starting to break a little bit. So if we think about LLaMA-4, and if LLaMA-4 is even more so like LLaMA-3, right? If LLaMA-4 gets to the point where even quantizing it to 8-bit is going to completely turn it to shit, then maybe we're doing inference in 16 bits, right? So I don't know anymore. It seemed like I was convinced that we were going to be doing inference in 1 bit, but now seeing the way that LLaMA-3 is compared to LLaMA-2 and LLaMA-1, I'm starting to think, okay, well, maybe we continue to do inference in 16-bit, right? And this even has implications for hardware, right? Because even GPU hardware is starting to specialize, right? So you're having GPU hardware that is specific for training, and then you're having GPU hardware that's specific for inference, right? And when you're designing your GPU, you kind of need to know at what precision you're going to be doing these things, right? When you're designing your GPU, you're deciding what the data types are in the GPU memory, right? So NVIDIA GPUs are designed for training. You need to be able to train on an NVIDIA GPU. So an NVIDIA GPU is going to have to support things like 16-bit or maybe 8-bit, right? I think you can do training on 8-bit. But an inference GPU like Grok, they're probably thinking, okay, well, if we don't support 16-bit and if we design our inference hardware such that it only works for 2-bit, it's going to be way, way faster than using a GPU that has 16-bit support with 2-bit. So that was kind of, I think, why you started to see a divergence of like, okay, we're going to have inference GPUs that only work with extremely small data types and are designed around really small data types because you're going to be using quantized models because they're only for inference. And then you're going to have GPUs that are designed for training that support these higher precision data types, but are much less efficient to use for inference because you have all this, you basically design the GPU memory around this higher precision data type. But if we're going to get, if this paper is correct and LLaMA-4 comes out and LLaMA-4 is even more sensitive to quantization than LLaMA-3, then maybe you're doing inference in 16 bits. And maybe LLaMA-5, you're still doing inference in 16 bits. In that case, then it doesn't sound as stupid to use an NVIDIA GPU for inference because the NVIDIA GPU is designed around these higher precision data types. So there's so much, the water is so turbulent in the world of like kind of hardware, inference, training, like what are we designing for? And I don't know, it's a tricky world. I don't have answers here. I'm just making guesses. You know, I don't actually know what future we're going to live in, but if inference is being done at the same data type and precision as training, then there's only going to be one type of GPU, and it's going to be the same GPU for training and the same GPU for inference. And in that case, NVIDIA wins, right? NVIDIA is going to basically dominate. But if quantization continues to improve, then you're going to see this bifurcation into training GPU companies, which is going to be NVIDIA, and then inference GPU companies like Grok. And in that case, then NVIDIA is going to lose a lot of market share because people are actually more interested in the inference, right? Really, what you care about is inference and actually giving some kind of service. You don't necessarily care about training, especially if everyone starts open sourcing their models, right? If no one's training their models anymore because Meta is open sourcing their models and Apple is open sourcing their models, then you don't actually need to do any training yourself, and you don't need to own any NVIDIA H100s, right? You just need to own a little cluster of Grok inference chips because that's how you serve your customers. So there's a lot of motion here, a lot of things that need to be determined. Yeah, you guys everybody loves talking about GPUs. No one likes talking about like little architecture tricks. Everybody loves talking about GPUs. Like I said it before, but the number one question that people ask is, "Hey, I'm building a computer. What GPU should I use?" It's like, you know, at the end of the day, humans are kind of materialistic and we love to purchase things. So everybody loves the idea of purchasing GPUs. So I don't know. I would recommend this system. This is a pretty good standard kind of like at-home system. But you know, if you got a bunch of money, if you got fuck you money, you should get yourself an 8x A100, 8x NVIDIA and H100. This is like that's the real setup right there. Purchase. Question from VFox. VFox is a beginner programmer. Should I start learning mobile development or website development? I don't know if those are necessarily the most useful types of programming to do. I would say, like, honestly, Python is really easy. Honestly, like AI and machine learning is some of the easiest types of programming, right? Because it's all Python, which is the easiest programming language, and it's a relatively simple like kind of flow, and there's so much activity and so many resources out there for you to learn from that I actually think that learning AI and machine learning is probably the easiest type of programming to get into if you're a beginner. So if you're a beginner, I would actually probably recommend AI. Nowadays, we ask, what's your GPU instead of what's your Lamborghini? I mean, I don't even have a 4090, guys. You know what? The dirty truth is that the best GPU I have in my house is a 3090. So I'm technically GPU poor. Okay. 10:30. Okay, we're pretty much done here. Let me sip some water, ask some more questions, and then I'll summarize the stream, and then we'll end it there. me see if I missed any questions. Scroll up here in the chat a little bit. Blah, blah, blah. Blah, blah, blah. Okay. Anyone know where I can get a pre-built GPU rack? So I'm not paid in any way by these guys, even though I mentioned them twice, but tiny grad. But I mean, I'm a fan of open source and I like what George Hotz is doing here, but this is going to be, I'm going to buy one of these probably, right? It's a box with like 8 or 6 GPUs on it. And whenever you're creating these kind of server racks, there's so much bullshit that you need to deal with, right? So like all of these are being connected through these PCIe slots. There's the kind of like, for example here, like when at the highest level, most people are just thinking about this. Most people are just thinking about GPU RAM, right? Like GPU, but there's so much more that goes into it, right? There's the bandwidth, the link bandwidth, how fast, which is basically like what is the speed of communication between this memory here and this memory here, this memory here and this memory here. Like the communication speed is almost as important as the total amount of RAM. And like figuring out all that shit, and for example, figuring out a power supply that can efficiently power that is a whole mess of shit. Like the power supply is a bigger problem than you think. Like when I've trained things here, like I will switch my breaker every time. So like if I have too much shit going on, like my house breaker will flip, right? So like having a good power supply, like designing all this shit, there's a good amount of time that goes into that. So unless you're like really looking to get into the nitty gritty of like system RAM bandwidth and like disk read bandwidth, you probably just want to purchase something out of the box. And if you want to purchase something out of the box, the easiest thing that you can do is just purchase one of these tiny boxes. But if you're not necessarily looking to drop $20,000 on a training box at home, you could just rent out on the cloud, right? Like this setup here, in this one, here, 8 NVIDIA 800s, like you can rent that, run your experiment, and you're going to rent that for way less than $10,000. So unless you know that you're going to be doing a ton of training over the next couple years, it's not actually a good idea to buy your own hardware, right? Just rent the hardware from the cloud providers, because the cloud providers are also subsidizing it for you. So they need to get users. So in order to get users, they subsidize the price. So whenever you go to a cloud provider and rent their hardware, you're basically getting money for free because they're basically giving to you this hardware. I don't know. I don't even know what I recommended there. Does all this make guardrailing LLMs more difficult? When you have fine-tuning data, does that mean you need orders of magnitude more data? No. I mean, generally, the data quality is more important. That's kind of what we learned here, right? Is that in this paper, they train on a very small amount of tokens, and the reason they're able to get a very relatively good performance, look at this. Like, so this is 3 trillions, Olmo, trained on 3 trillion, and it's a bigger model, has a lower score. OpenELM, here, it's a smaller model, 1.1 billion parameters, trained on less tokens, and you're getting a higher score. So it's not the data set size. The data set size is important, but the data quality is also important. You need both of them. And if you can just improve the quality of your fine-tuning data set, you're going to get a lot more bang for your buck than if you just kind of like mindlessly add more fine-tuning data. It's a 2-computer system, 1 big training agent. Okay. All right, I think that's all the questions. Let's summarize this. I'm already late. Thank you for the support, man. I appreciate that you liked the content. All right, here's a summary. Today, we reviewed three different papers that came out on open source models, specifically kind of smaller open source models. We had OpenELM, Phi-3, and LLaMA-3. OpenELM is Apple's small model. So this is a 1.1 billion parameter model that has been trained on a very small amount of tokens. It uses all of the kind of standard tricks, such as pre-normalization with RMS norm, rotary position embeddings, grouped query attention, flash attention. And the kind of one special trick that they choose to highlight here in this paper is this idea of layer-wise scaling, where you are basically changing or not using the same amount of heads and the same width of the multi-layer perceptron in the feed-forward network. You're changing the number of heads and the width of that for every single block in your architecture, right? Because your transformer architecture is going to be a bunch of these blocks all together. The main kind of thing that they do here, which I find interesting, is that they heavily filter and curate the data sets, right? So rather than just training on refined web and pile and red pajama, they create these subsets of the data sets, and those subsets, which are technically less than they were doing before in Olmo, you're getting better performance. So the moral of the story for this paper is that dataset curation is important. Okay. The next paper we read was Phi-3. This is Microsoft's small model, right? So this is a 3.8 billion parameter model trained around 3 trillion tokens. The story here is also that dataset curation matters. And in here, they go a little bit, they get a little bit more in detail. And specifically what they talk about is that you want to curate your data set such that you don't spend too much capacity, right? Model capacity, you can think of it like how much information can this model compress. So you don't want to be spending too much of your model capacity storing factual knowledge. What you really want to do is to curate your data set such that it's like data that improves the reasoning ability of the model, and then just assume that when you deploy this model, you're going to deploy it with a search engine. So you're going to deploy it such that the model has access to some tools. Some of those tools might be a calculator. Another tool might be a search engine. So I really like this idea because I think it's really powerful, where make the language model just a kind of a reasoning engine, remove all this factual knowledge, such as the result of a Premier League game, or like just a bunch of like 2 + 2 = 4, 4 + 4 = 8, like that type of shit. This type of like factual knowledge is not actually useful. Remove all of that from your data set, train on this kind of reasoning logic type data, which you can synthetically generate, right? And we know that LLaMA-3 is synthetically generating data. We know that Microsoft is synthetically generating data. We probably know that OpenAI is synthetically generating data. They're just not open, so they're not telling us, but we can kind of assume that they're doing that. But train your model on that, and then assume that the factual knowledge can be retrieved via some kind of RAG or some kind of search engine tool. Okay. I guess one other extra thing to say, both OpenELM and Phi-3 are still using the old tokenizer. So they're still using this old LLaMA-2 tokenizer with a 30K vocab size, but we now have a better tokenizer with 128K vocabulary size. So you could do that. You could take this and retrain it with the better tokenizer, and you would probably get a better score. So 6 months from now, I expect Phi-4 to use the better tokenizer. All right. The last paper that we looked at was this Quantized LLaMA-3 paper, which came out like almost immediately following the LLaMA-3 paper, or the LLaMA-3 release, which means that these guys were waiting. They had all the code ready. They had the paper basically written. They just had the tables were empty. And then as soon as LLaMA-3 came out, they plugged it in, they ran it, they filled in all these tables, then they wrote the conclusion, and then they published the paper. So the iteration, the like speed of like paper publishing is absolutely insane now. But in this paper, they basically try to quantize LLaMA-3 with every quantization method that they could find. So here are all the different types of quantization. And you see kind of the general pattern where LLaMA-3 at full 16-bit precision gets the highest score, and then you can quantize it to 8 bits, 4 bits, and get pretty good, 68, 64. Here's another 4-bit at 68. 8-bit 68. So quantization is still definitely working. You can still definitely reduce the size of your model and improve the speed of your model, especially if you're going to be running it on a cell phone, right? And get pretty much the same performance. But the one kind of interesting thing that they talk about in this paper is that they noticed that no matter that LLaMA-3, if you quantize it, will never be as good as the original LLaMA-3 16-bit, which is different from LLaMA 1 and LLaMA 2. In LLaMA 1 and LLaMA 2, you could quantize them and then LoRa fine-tune them, and they would be basically better than the original FP16. But it seems like LLaMA 3, you can't do that. If you're never, like, no matter what quantization technique you use, you can never beat the original LLaMA 3 16-bit, right? Look at that, 75. That's a strong. Actually, I don't know, look at this, RTN 74, but still not as good as 75. So this is changing the picture. And to me, the narrative in this paper was that, like, okay, maybe quantization isn't a magic wand. Maybe we're not going to be able to quantize down to 1.1 bits, 1 bit. Even though we're seeing good results with that, maybe LLaMA 4 will be even more fragile and LLaMA 5 will be even more fragile. And then maybe this whole narrative that we've been spinning around quantizing things and sparsifying, maybe that was something that we could do before because our models were kind of undertrained, right? They had too much capacity, the data set wasn't big enough. But now that we have models that have even less capacity and they're trained on even more tokens, the quantization doesn't work as well, pruning doesn't work as well, and we talked a little bit about the implications that has for GPUs, where if quantization works well, then you have this bifurcation into inference GPU hardware and then training GPU hardware. But if quantization doesn't work as well, then maybe all GPUs are kind of the same, because whether you're doing inference or training, it's all being done at 16-bit precision. So I don't know. There was definitely implications here in this paper in terms of the future of the GPU market and the future of kind of whether we use quantization at all. But that's basically it, guys. 3 little short papers about small open source models. And TLDR, data is important. TLDR, make sure you curate your data. Think about what exactly you're getting your model to learn. And then think a little bit about whether you should be quantizing your model and whether you really want to quantize your model. This has to do with density. Good got better. Appreciate. All right. Everybody's saying thank you. I'm going to say thank you as well. Thank you, Majedi, Tarun, Lil KM, Timothy, Work, Zorg, Godbuddy, Ed, Jai K, Saskia Ludin, IRX, J Kai, Work. Who else? Max Mali, 87GN, Sarah, Zorg, Tarun, Cheb Khaled, VFox87, Ed, Khalil, Max. I don't want to miss anybody. IRX, blah, 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 blah. Snooks, Oma Viva, Work, Mito, Economic Sanity, 2ARX, James McLean, and Aries. Thanks, everybody, for listening. Tomorrow, we're going to be doing a little stream on robotics. So if you're interested in robots, we're going to be reading a little bit of a fun paper. It's on basically robots versus animals and comparing kind of the performance and the speed and the control mechanism. So if you're into legged robots and animals, check out tomorrow's stream. If not, have a great weekend. Thanks, everybody, and see you guys later.